Just a reminder about test number 4 on Thursday. Okay, so it'll cover what we are doing now and one more section, which is mostly computational. So it's nothing conceptually heavy in any of these. So yesterday we were doing sections 4.2 and 4.3, in particular Gaussian elimination. Okay. To solve a m by n system, that is m equations and n variables. So the process is to write the augmented matrix, reduce it to REF. So Gaussian elimination to solve Ax equal to B. So A is the coefficient matrix, X is the vector of unknowns, B is the right-hand side. This is the augmented matrix, which is a m by n plus 1 matrix. Okay. That's the corresponding row echelon form, and then you back substitute. I think that's one word, back substitute. And solve for all the variables backwards, xn, xn minus 1, and so on. And there are 3 possible scenarios for any linear system. You could have a unique solution, which means there are no free variables. Okay. That's what our first example was about. It's kind of straightforward. You have 5 variables, you just solve for it one after the other, you get exactly one set of answer. Okay. It's also possible that there is no solution. That is what you call as an inconsistent linear system of equations. Okay. The way to spot that is if you look at your REF, and if the one of the rows looks like this, 0, 0, 0, and then some non-zero number here. Okay. That means it's not solvable. Okay. And the third scenario is the more important one, infinitely many solutions. And which means that there is at least one free variable. Okay. No free variables means there is only one solution. Infinitely many means there is at least one free variable. And since this is a concept that is going to be carried over into the next few sections, okay, we're going to emphasize on this particular part. This is what we are trying to focus here. And the way to look for the free variable is if in your REF, the columns with the leading one those are called the pivot columns. Those variables are the ones which are basic. If you understand this concept, most of chapters 4, 5, even 6 and 7 are pretty much straightforward in terms of the computational part. And the remaining columns without any leading ones are the non-pivot columns. Those are the free variables. Again, there is no guarantee that there is more than one. So it's basic variable or variables, free variable or variables. And the idea is to solve for the basic in terms of free always. So even when we are doing the homogeneous system today, we're going to follow the same process, okay? Except that the right-hand side is going to be 0. There is nothing different in terms of what you're doing procedurally. So solve basic in terms of free variables. So that's where we stopped. So just to make sure that all of you understand what is going on, let me ask you a couple of pop quiz questions. In this matrix here, this is already an REF. You don't have to do any calculations. 1, 2. How many variables are basic and how many variables are free? I'm not asking you to solve it. Okay, that is something you could do easily once you. This is not the augmented matrix. If you want the augmented matrix, just put it like this. How many basic and how many free variables? Let's first ask the people online. What do you think? So I'm expecting numerical answers here. Don't tell me answers like 55.3 or all of them are basic. What about you people? What do you think? All of them are basic because they all are pivot columns. Okay. So there are no free variables. So how many solutions will this have? Just one solution. Okay. I don't know what, but exactly one solution. This is what linear algebra does. It gives you a good idea about what to expect, even if you're not able to give the answer immediately. At least you know what is coming up. Okay. So there is no free variable. Exactly one solution. Okay. All variables are basic in this case. Good. What about this one? Now you have to start counting. So there are 2 equations and 8 variables. Okay. It's possible. How many basic variables and how many free variables? All right, let's listen to.
2 basic, 6 free.
Okay, so somebody here says 2 basic and 6 free. Let's ask online. What do you think? I'm not saying you're wrong. Okay. Agree? Any disagreements? So the answer so far is 2 basic, which I hope are these 2. And all the remaining ones are free because there are no leading ones. Yeah. Is that yes or no? Or yeah? Seem to be suspicious. It is, right? This is a leading one there. That's a leading one here. So it looks kind of awkward sitting down here, but that's okay. So x1 and x, what do you count this? 1, 2, 3. Yeah, x8 are basic. So there are 6 free variables. Okay. So if somebody is asking you how many solutions will the system have, what is the answer? Infinitely many. Okay, it shouldn't be 6. 6 is the number of free variables. Tells you there are infinitely many solutions. That is one thing that you should kind of take away from this course. If somebody is asking you how many solutions are there for a linear system, it should be one of those answers there. Okay, shouldn't give intermediate answers like 35 or 12. Okay, so it's either 1, 0, or infinitely many, always. All right, so if this concept is clear, let me make sure. Any questions about this? All right, let's talk about homogeneous systems. Okay. I hope all of you got a chance to do the homework and start fighting with all the matrix operations. Don't wait till Thursday morning to do it. Okay. Yeah, homogeneous systems. This is what we'll be mostly doing for the rest of the semester. Okay, so we need to get a good grip of what is going on here. The only difference between homogeneous and non-homogeneous systems is that the right-hand side is equal to 0. Now that doesn't mean that there is nothing to look for in this particular case. Okay, there are lots of interesting cases here. So question is what to expect. One situation is that there is a unique solution, okay, which means there are no free variables. If there is a unique solution to this system, what is that solution? What is an automatic answer to this system here? It's 0, right? I mean, a times 0 is 0. So if the solution is unique, that solution is the 0 solution. Because there is only one solution, and x equal to 0 is always a solution. Okay, so that is the only solution. That's a super boring case. Okay. So obviously we are interested in the second scenario, or what is the other possibility? Infinitely many solutions. Which means there are, or there is, or there are free variables. Okay. How is it possible for Ax equal to 0 to have infinitely many solutions? The easiest example is this. If we have, say, x plus y equal to 0. Okay. One solution is 0 plus 0 equal to 0, but then there are other solutions, 1 minus 1, 2 minus 2, 3 minus 3. You can sit here and generate infinite number of answers. Okay. So this has got infinitely many solutions. Even if it's homogeneous, okay, the fact that one of these variables is free, you can write x equal to negative y, that y is a free variable. So it starts from a grassroots level, and that expands into how many ever equations and variables you have. Here is my question to you. Why am I not concerned about an inconsistent system here? I just wrote two cases. In this case, I had a third situation, inconsistent. Right? Why am I not writing that here? Yeah, so the right hand side is equal to 0. Okay, that cannot mutate into something that is non-zero ever. Okay, so there is no question of an inconsistent homogeneous system. Okay. Write it clearly. X equal to 0 is always consistent. It's a question of these two. It's whether it's unique or infinitely many. Okay, it's always consistent because the right hand side is just a bunch of zeros. That 0 is not going to become a non-zero number by just adding or multiplying things. Okay. Always 0. So that even if there are zeros on the left hand side, the augmented side is always going to look 0. That is not going to change into 1 or 5 or anything. So that also means that when you're writing the augmented matrix, you can stop writing this extra column of zeros because it's not really adding any value to your calculations. Okay. That's your choice. So you can skip the 0 augmented column. Just make sure that you remind yourself that you have the original matrix when you're doing the calculations. Again, that's something that's a personal choice. If you want to write the column of zeros, I have no problem with it. Okay. All right, so let's do a couple of examples. Okay. The same raw operation, so nothing has changed here except for the right hand side. And the only problem is I have to now find the correct document here. 1 minute. Should have done this earlier, sorry. Sure. Almost there. Yeah. Okay, so here is the example. Solve the following homogeneous system and write the solution in the vector form. So if it is a homogeneous system, obviously you should expect free variables, otherwise it's the super boring case. Okay. So x1 plus x2 minus x3 plus x4 equal to 0. x1 minus x2, copy this carefully, it's all plus minus signs. Plus x3 minus x4 equal to 0, and x1 plus x2 minus x3 plus x4 equal to 0. So can you write the matrix? As I said, the augmented matrix is not mandatory here because the right hand side column is zeros, but you can write it if you want. Okay. So write that, do your operations, and identify the basic and free variables, okay, and write the solution. Did I copy the same equation? Sorry, let me see. Give me 1 second, okay. Oh, this should be a minus here. So thank you for pointing that out. Otherwise, it would have looked the same equation. That was not a trick question. Okay. This x2. So for starters, if you want to write the augmented matrix like you did earlier, you could write this, but you could kind of cut off this last part. Okay. So that's what the matrix will look like without the augmented column. Okay. If you do that, don't put another separator line there. Okay. So just be careful. If you're cutting out the augmented part, you shouldn't do this. Okay. Did I do this right? Or I was about to do it wrong. I spotted something. Then -1/2 or 2 and 1/2 or 3. How many free variables do we have? Any answers online? Somebody here said 1. How many free variables? If it helps, I can circle the leading ones. That might give away the answer, but those are the leading ones of each row. Okay. All right, now cannot be 0 because there's an extra column. So there has to be at least 1. Okay. We don't have enough rows and columns to make all the variables basic. So the question is where it is and how many. If it is a non-square matrix, it has to have some free variable somewhere unless it's inconsistent. Okay. So this is a leading one for the first row. That's a leading one for the second row, leading one for the last row. The third column is kind of left without anything. Okay, so x3 is free. Please don't mark this as a leading one. Okay, that is not leading. It's a 1 or -1, but it's not leading. All right. Hope that is clear. Any questions about why x3 is free? Or and if you got 2 free variables, it's possible that you made a small mistake with the plus minus signs. It's a confusing matrix, I know. All right, so what does row 3 give you? Now you're starting to solve it backwards. Okay. Remember that it's a homogeneous system, so the right hand side is 0. So what is the result of row 3? x4 equals 0. Just x4. I'm not saying the entire x equal to 0. x4 equal to 0. Now go to row 2. And that will give you x2 minus x3 equal to 0. So x2 minus u. Remember that x3 is free. Okay. So x2 is u. You're solving basic in terms of free. And row 1, sitting with its full glory, x1 plus x2 minus x3 minus x4. x4 is 0. Okay. Equal to 0. So x1 is equal to 0. So if you write your solution now, x equal to x1, x2, x3, x4. And there's only one free variable, so it's going to look like one column here. So x1 is 0, x2 is u, x3 is u, x4 is u. 0, u, 0. And if you're still just getting used to this concept of free variable, all that is saying is that any multiple of this vector is a solution to the system. Okay. So this is a free variable, means that any multiple of the vector 0, 1, 1, 0, that's a vector in R4 because it's got 4 components. Okay. Of the vector 0, 1, 1, 0 is a solution to our system. That includes u equal to 0. Okay. Obviously, it's a homogeneous system, so that's always a solution. But there are others like this 0, 1, 1, 0, 0, 2, 2, 0, 0, 3, 3, 0, and so on. Okay. All right. Any questions about this? So the same process and everything except that right hand side is 0. Okay, so you can work with a smaller matrix because the augmented side is not there. We'll be doing the the homogeneous system later with different terms and other things in chapter 5, but the same process we'll be doing there, so please don't forget this. All right, so let me give you a couple of conceptual problems to work on. Okay, this is where linear algebra gets all attractive. These problems are nice, so nothing wrong about these, but just check whether you understand everything you're doing. Okay, here is one example. Please do this carefully. Okay, I'm expecting you to know these kinds of problems for test number 4. So here is a question. I'm just going to mark it as a separate example. Okay, given the following system, x1 minus 3 x2 equal to 1, and 2x1 plus h x2 equal to 2k. So find the values of h and k if case 1, the system is, or the system has a unique solution. Case 2, no solution. And case 3, infinitely many solutions. This is where linear algebra is kind of really testing your understanding of what you're learning. Okay, all those examples are nice. Calculations are always important in linear algebra, but also are these kinds of problems. Okay? So can you try to look at this system? It's a 2x2 system, so it's easy to manipulate. Okay, you can write the augmented matrix and start with the REF. That will be easier to work with instead of playing with the equations. So my suggestion would be to first write the augmented matrix, do the REF, and then try to answer these questions. Just take a few minutes and try that. You don't have to answer these in the same order. You could do maybe 3 first, 2 second, and 1 last, depending on which is easier. Okay. All right, so the key thing is to not freeze when you see this problem. Okay, so just do what you know, which would be to write the augmented matrix, do the REF. Okay, of course, it looks weird with the H and the K in it. That's part of the game. And then you try to go back and think about what we are trying to do here. Okay, first, let's try to eliminate this thing, the case with no solution. That is the one which has a very clear structure to your REF. Okay. So what values of H and K will cause problems here where you have 0 equal to a non-zero situation? Yeah. When H is -6 and, well, that is by itself is not enough, right? And K is not equal to 1 because you could have 0, 0, 0 here. That's okay, right? So case 2 is easier to answer. The system is inconsistent or no solution. If H is equal to -6, so it's hitting a sweet spot of that one particular number of -6, and so it has to come with another case here, and K is not equal to 1, because if K is equal to 1, you have 0 here. Okay, so you have 0, 0, 0. That's okay. What you don't want is 0, 0, and a non-zero number here. Okay, because this will cause 0, 0, and a non-zero number in the second row, okay, which is what we mean by saying an inconsistent system. Okay. So for example, if H is -6 and K is equal to 2, that will cause 0, 0, and then 2 here. But if k is equal to 1, we are okay. Is that clear to all of you? This is how you should approach these kinds of problems. Okay, so write down the augmented matrix, do the REF, and look at the different scenarios. Okay. This is the easiest one to get out of our way because you don't want 0, 0, non-zero. All right, now let's do the case with infinitely many solutions. Okay. Case 3. Remember that when the system is having infinitely many solutions, there must be at least one free variable. Okay. That is the concept that should hit you immediately, that if there is a free variable, there are infinitely many solutions. Okay. So let's go back to the same REF, 1, -3, 1, and 0, h plus 6, and 2k minus 2. So this leading one is already here. So x1 cannot be free. Okay. In what situation will x2 be free? Can somebody online try that? When h is equal to -6, what about k? K equal to 1. Okay, so whatever we are trying to avoid there is the situation here, right? So when h is equal to -6 and k equal to 1, in that case you have 0, 0, 0. It's consistent and there is a free variable. Okay. This becomes 1, -3. You don't have to write the analysis of why it is, but I'm just showing you if h is -6 and k is 1, you have 0, 0, 0. Okay. So that is basic. This is free. And it's consistent because 0 plus 0 is 0. Okay. So you have the case for no solution and infinitely many solutions. What about the case with just one solution? H equals set only value. Theoretically, what will include the case with unique solution? Whatever is not in cases 2 and 3. Do you agree? You should stay out of 2 and 3 for 1. Okay, because it's a trichotomy, right? So anything which is not in cases 2 and 3. Well, what will that be? H is not -6. And now comes the tricky part. So h is not -6 will make sure that both variables are basic. Okay. What about k? Is there any restriction for the value of k? No. Okay. K could be anything. And any value of k. Okay. So give me any number which is not -6 for h, and any value of k, I have a unique answer. May not look nice, but I have a unique answer. Okay. So just to show you, a freak example would be when h equal to say -15, because that's not -6, and k equal to 7. Okay, nothing special about those two numbers. You have 1, -3, 1, and 0. -15 plus 6 is -9, and 2 times 7, 14 minus 2 is 12. Okay. And you can divide the second row by -9. So it's 1, -3, 1, 0, 1, -12/9, which is -4/3. So you have two basic variables. So x2 is -4/3 and x1 -3, x2 is 1. So you can, so that is a unique solution. So any combination of these two will guarantee just one solution. All right. Any questions on this one? Do it again when you study for the test, okay, which is day after tomorrow, actually. There is one more example of the same flavor, in case you want more for practice. Actually, I asked this last spring semester in one of the tests. It went pretty okay, so I'm assuming that it was not a very cruel question. So given the following system of equations, x -3 z equal to -3. What would be easier if I'll just project the screen and share the screen for people who are online. Okay, I think that might, because it's a lot of writing. If you can just copy that part, don't look at the answer now. So that way I don't have to, let me just pull the screen down for you guys. So I gave them all these things, okay. I gave the system, I also simplified the matrix in the REF form, so they didn't have to waste time doing all that stuff. So I'm essentially asking them the same set of questions. Find the only value of k where there's no solution, more than one solution, and a unique solution. You don't have to write all the stories in between. You don't have to verify these off. Just write the system, the matrix, and the questions. In spite of those instructions, some students wasted time trying to get the REF. So that's a different story. All right. Can I, all of you got the question? All of you got here? People online, can I stop sharing if you don't mind, or anybody wants to stay there for a few more seconds to write it down? You can start trying. Okay, so the REF is given, so you can just start from there. K square plus 3K minus 10 was the row 3, column 3 position. Okay. All right, so let's slowly start with the first one, the case with no solution, which is probably the easiest of the 3 questions there. Okay. Remember, no solution if this is 0 and this is not 0. Okay. That is when no solutions happen. Well, when is K square plus 3K minus 10 equal to 0? I'm not going to ask you the solution for this, right? K plus 5 times K minus 2 equal to 0, K equal to negative 5, K equal to 2. The question says find the only value for K. So why do we have 2 values? Yes, so if K equal to 2, 4K minus 8 is 0, okay, that is not a problem. So this is okay. Because 4K minus 8 is equal to 0, 4K equal to 2, and there is absolutely no problem for having 0, 0, 0, 0. That is consistent. So that is not our problem here. Our problem is this one. Okay. So when K equal to negative 5, the system is inconsistent. Because then you have 0, 0, 0, non-zero. All right. So that is one thing to avoid when we write the solution for the unique part. Right? Next case is when do we have free variables? Infinitely many solutions. This should be done carefully because there might be hidden situations in there. Okay, let's do the obvious one first. So when could there be free variables? Can somebody online try this and tell me? What happens when K equal to 2? That is the value that we kind of avoided here. Okay. You have 1, 0, negative 3, negative 3, 0, 2, 5, 4, and 0, 0, 0, 0. Of course, you could divide the second row by 2 to make it a perfect REF. Okay. So what do you think? Is X3 free? Yes. Okay. So if K equal to 2, there is a free variable, which means there are infinitely many solutions. Is there any other value of K where this could happen? K equals 0. You have to look carefully why that is true. Okay. If K equal to 0, you're just trying to make sure that x2 is never a free variable, but unfortunately it could be. Okay. If K equal to 0, we have 1, 0, negative 3, negative 3, 0, 2, sorry, 0, 0, 5, 4, and 0, 0, negative 10, negative 8. So plugging in K equal to 0 into that matrix gives you these numbers. This is consistent because you could divide the second row by 5 and make it 1 here, 4/5 here, and the third row by -10, and that's going to be 1 here and -8 over -10, which is 4/5. And then you could do R3 minus R2. So there is no question about the system being consistent here. Let me know if I'm missing up any numbers here. Okay, I'm doing it fast. Is there a free variable in this case? Which one? Second one. I know it's a little bit not obvious. Okay, this is the leading one for the first row. The leading one for the second row is down here. Okay, the second column is kind of staying free of any kind of leading ones. Okay, so X2 is free. There is no leading one in the second column. Okay, which you have to kind of look carefully to spot that one. So for both k equal to 0 and k equal to 2, there are infinitely many solutions. Okay. Now the easy question, what are the values of k we should avoid to get a unique solution? K must not be equal to what, and what. Yep, just all these three bad guys, right? 0, 2, and -5. And once you avoid those cases, part C, that's a unique solution. So the guarantee is that it's a trichotomy. There is no overlap between these cases. Okay. Once those two cases are clearly identified, unique solution exists if k is not equal to 0, 2, or -5. So it could be 1, it could be 3, it could be 4, it could be pi, e, whatever you want. Okay. All right, so you can expect one of these creatures on this test. Okay. Don't try to get all innovative. Just start with the REF. The answer will follow soon. Any questions about any of these? This is almost end of 4. Let me just define one more thing and then I'll move on to 4.4. Any questions about this? There is a small definition in 4.3 which kind of reappears later. So I'm just going to define it once and I'll make use of it in other sections. Okay. The rank of a matrix. So if you looked at the textbook, you probably saw this word and you were wondering, what is this? Okay. The rank of an m by n matrix is the number of, please write this carefully, okay, number of non-zero rows in the REF or the RREF of the matrix. If there are two parts to this statement here, one, you're counting the number of rows which are not just full of zeros, okay, and you count it where it's in the REF, not in the original matrix. Okay, so don't just take a matrix and start counting the number of rows. That's not going to do it. You have to first get the REF and then count the number of rows. Okay. So there are a couple of examples just to show how this is done. A equal to 1, -2, 3, 4, 5, 2, -4, 6, 8, 10, and 3, -6, 9, 12, 15. Find the rank of A. So if you are not careful about what you are reading from the definition, you will say, oh, there's 1, 2, 3 rows here, the rank is 3. No. Okay. Next part in the REF. Can you write the REF for this matrix and see what the rank is? If my mental calculations were correct, you should do it pretty fast. All right, any answers? One. So somebody here said 1. Can people online agree or disagree? Agree? Okay, so the REF, I hope, is not too complicated. Let's do R2 minus 2R1 and R3 minus 3R1. That's 1, -2, 3, 4, 5. And my plan was to get a bunch of zeros here. And that is okay. That's an REF because there's a 1 up there, 2 rows full of zeros. You're counting the number of non-zero rows, not the number of zero rows, so the rank is 1. Rank is a positive integer. Okay, you shouldn't be having ranks like 3.5 and so on. Okay, so it's counting the number of things. This is 1 non-zero row. So as long as you don't make the mistake of just counting the given matrix as such, you're okay. What does the rank tell you? Well, if you have an m by n matrix, okay, so suppose A is an m by n matrix, which means you have m rows and n columns. Statement A, if the rank is equal to m, which means there are no rows full of zeros. Okay. That is what it means, right? All the rows have something or the other than zeros. Okay, it's called the full rank, which means everything has something in it. Okay. What can you say about the system of equations Ax equal to b? Is it consistent or inconsistent? As a guaranteed statement. Okay. There are no rows full of zeros. So what do you think about the system? Is it always consistent or is it doubtful? It's always consistent, okay, because this has no rows full of zeros. Okay, so the system Ax equal to b is always consistent. Because inconsistency happens only if there is a row full of zeros and it's equal to a non-zero number. Okay, so if that situation is not there to begin with, there is nothing to worry about. And if the rank of A is equal to n, you don't care if m is more than n or n is more than m. Okay. what do you think can be a safe statement to make, which is always true? The rank is equal to n. And it's okay to be not correct, because it's the first time you're saying this, so you can make a guess and, it's okay if it is wrong. So one thing is that the system is still consistent. Okay, so what else can be guaranteed here? Every column has a leading one. Okay, without that, you cannot have rank equal to the number of columns. Okay, every column should have something in it. So every column, yes. So the answer is that it must have a unique solution. No free variables. Okay. That is especially true for a square matrix, because in that case, and if the system is consistent, there is no free variable at all. All right, so those are two applications of the concept of rank as a predictor of things to happen. Okay, but right now we don't have a lot of other things that we have done in this. So at this point, I don't expect you to do a lot of things with rank for test number 4. Okay, this will come up again in test number 5. So just keep those definitions handy. So don't forget these things. Okay. Test number 5 will be a little bit more conceptual because of some of the definitions that creep up there. So don't throw it away after test number 4. Okay. All right, so now you should be able to do your 4.2, 4.3, all the homework questions, and make sure that all of you are comfortable with all the matrix operations. Okay. The last section that you should be responsible for test 4 is the next one, which is a pretty easy section if you are careful about your calculations. Okay. Inverse of a square matrix. Emphasis on the part of the square matrix. So we are kind of moving away from m by n matrices to n by n matrix. Okay, so let A be an n by n matrix. So that's in general. Okay, n rows and n columns. We define the inverse of A denoted by a to the power of -1. Okay, you don't write 1 over a, just as a tradition, you don't write fractions for matrices. Okay, so we define the inverse of a denoted by a to the -1 as an n by n matrix such that product A times A inverse is equal to A inverse times A, and that's equal to, what should be the answer there? Remember that you multiply a number with its reciprocal, okay, you get 1, right? So there should be something equivalent to 1 here. The identity matrix, okay, the n by n identity matrix. Okay, that is the equivalent of 1 in the world of matrices. Okay, and that is the matrix with 1s along the main diagonal and 0s elsewhere. That's 1 0 0 0 0 0 1 0. So it's a triangular matrix, it's a diagonal matrix with ones along the main diagonal and zeros elsewhere. It's also in RRAF form. So such that this, if it exists, okay, so this existency part is something that we will worry about in section 4.6. So today we're going to just assume that whatever matrix we're going to do has an inverse. Okay. So that's a bigger question of sort, which we'll concern about later. All right, so to find the inverse of a matrix, okay, going to do two cases, a 2 by 2 and a 3 by 3, which is probably the biggest you want to do by hand. After that, you want to make use of MATLAB or something. 2 by 2 case. So that A equal to A11, A12, A21, A22. The good thing is there is a formula for this. Okay? Unlike a 3 by 3 and a 4 by 4, for a 2 by 2, you can write a nice, not so crazy formula for the inverse. Okay? The inverse, A inverse is given by one over A11, A22 minus A12, A21. So that's a number. Okay, so you multiply these two. Some of you may be thinking about some terms or some names. Don't think about it right now. Okay, I'm not using any names. Multiply those two, subtract the product of those two. Okay. Times this 2 by 2 matrix, which is obtained by just interchange those two positions, A22, A11, and change the sign of the other two, negative A12, negative A21. Okay, so if you multiply this with this matrix and divide by this quantity here, you will get the 2 by 2 identity matrix. You don't have to check it, but if you have plenty of time to do it, okay, you will get 1, 0, 0, 1. Okay, so for a 2 by 2, it's just plug and chug, right? So for example, if you have A equal to 2, 3, negative 4, 5, okay, some 2 by 2 matrix. A inverse is 1 divided by 2 times 5 is 10 minus the product of those two is negative 12. So again, interchange those two. So the 5 goes to 2, 2 goes to 5. The 3 becomes a negative 3, negative 4 becomes a 4. Of course, 10 minus negative 12 is 22, and you're done. Is this inverse always defined, or is there some condition that we should satisfy based on what I wrote there? Is there anything that you need to look out for? Yeah, the denominator cannot be equal to 0. Okay, so note that A11, A22 minus A12, A21 should not be equal to 0 for A inverse to exist. So for example, if you take this matrix 1, 2, 1, 2, okay, this has no inverse because that product is equal to 0. Okay. So you say it's not invertible. There is a name for that product and the difference of those products, which we will not use right now. Just delay that term till tomorrow. All right, now the 3 by 3 case. This is the one that you need to get used to. It's called the Gauss Jordan algorithm. or method. Okay. And all of you will get one chance to do this on test number 4. So here is, I'm just giving you a question, so all of you know one question at least. Okay, and this works for any bigger matrix, but it's kind of insane to do this by hand for 4 by 4 and 5 by 5. So this works for any n by n matrix. Idea is this. So we want A times A inverse equal to the identity matrix. Okay, so the idea of Jordan was to sort of flip it over. So start with the augmented matrix. A augment I. Now that you might think, okay, that's a crazy big matrix. That's what I said. 3 by 3 itself is large because you got a 3 by 3 on one side, augmented with a 3 by 3, got a 3 by 6 matrix. Okay. So start with the augmented matrix, do the RREF for this, convert the left-hand side into its RREF, which is going to be your identity matrix. And whatever you get on this side is automatically going to be your A inverse. Guaranteed. Again, today we are doing problems which are guaranteed to give you inverses. So assuming these are all nice matrices, okay, if you do the correct RREF for this particular augmented matrix, the right-hand side here would be the A inverse. So that is the method or the algorithm behind the Gauss Jordan process. So if, of course, if you get one example, you get the idea because it's just a bunch of raw operations. Okay, so you just need to get used to it. So let's do an example right away without wasting time. So I'll do the first one and then I'll let you do the second one and have fun with it. All right, so let's do this carefully. Copy the matrix correctly so that you won't end up into some kind of crazy infinite loop. Okay. It's a problem where you could easily make mistakes, but don't panic if you make a mistake. You just go on with it and finish it. Okay. Especially if you're running out of time, don't try to restart it and that'll make it worse. I'm pretty forgiving with calculation mistakes. I usually take 1 or 2 points off. That's a maximum. So don't panic if you make a small mistake somewhere. So find the inverse of the following matrix. A equal to 1, 1, negative 1, negative 4, negative 3, 8, and negative 3, negative 6, negative 8. Two things. First thing, the inverse is not just the matrix with the reciprocals of these numbers. Okay. Second thing, there is no shortcut formula like you have for 2 by 2. So you have to do this algorithm at this point to get the 3 by 3 inverse. Now here are some of the common mistakes that happen. First of all, you have to copy this correctly. Okay. So the augmented matrix with the identity matrix of the same size will look like this: 1, 1, negative 1, negative 4, negative 3, 8, and negative 3, negative 6, negative 8, 1, 0, 0, 0, 1, 0, 0, 1, 0. These are some of the bad things that you could do to this problem. Okay, what is wrong here? Yeah, that's the wrong identity matrix. If you do these kinds of mistakes, I have no sympathy. But if you make a calculation mistake at 2 plus 3 equal to 6, I can forgive it. Okay. So start with the correct identity matrix. Remember, our objective is to convert this into an I. Okay, so do whatever is required to get this into the identity matrix. Do the same process here. So R2 plus 4R1 and R3 plus 3R1. The whole point of augmenting is to make sure that you do it on both sides. That's 1, 1, negative 1, 1, 0, 0. R2 plus 4 R1, that's 0, 1, 4, 4, 1, 0. And R3 plus 3 R1 is 0, negative 3, negative 11, 3, 0, 1. So made some progress there. And as always, if you get some nice things, don't lose it. Okay? You don't want to go back and forth in infinite loops. Let's do R3 plus 3 R2. 1, 1, negative 1, 1, 0, 0, 0, 1, 4, 4, 1, 0, R3 plus 3 R2, 0, 0, 0, 0, lottery 1. That's going to be 3 plus 12 is 15. 3, 1. We're doing okay so far? All right, so looks like the lower part of the identity matrix is here. Okay, this part is all set. Please don't destroy it now. Okay. The last thing you want to do is, kill all that and start over. Now let's take care of the upper part of this. Okay, can somebody tell me one possible way to make some progress here? We're looking for an RREF, okay, not an REF. So how can we get more zeros above those leading ones? Any suggestions? Yep, R1 minus R2. So it's 1, 0, negative 5. And you have negative 3, negative 1, 0. And we did not change anything else. 0, 1, 4, 4, 1, 0. I've been writing this 4, 1, 0 for a while now. 0, 0, 1. 15, 3, 1. Got two more targets here, right? This negative 5 and this 4. Take care of those and we are done. How can we take care of the negative 5? Somebody online? Any strategies which won't kill any other nice things? R1 plus 5 R3, good. So looks like all of you are now ready for your next test. So 1, 0, 0. Okay, let's do this carefully. R1 plus 5 R3. That's going to be negative 3 plus 75. That is 72. Okay, 15 times 5 is 75. Then you have negative 1 plus 15. That is 14. And so plus 5. Still 4, 1, 0. Losing focus. 0, 1, 4, 4, 1, 0. and 0, 0, 1, 15, 3, 1. One more to go, right? Since it looks like all of you get the idea, I'm just going to do that myself. R2 minus 4R3. Again, if you spot any mistakes in what I've written so far, please feel free to interrupt. Okay. 0, 1, 0. R2 minus 4, R3 is 4 minus 60, that is negative 56. 1 minus 12 is negative 11, and negative 4. Are all those numbers correct? So this is the 3 by 3 identity matrix. And the Gauss Jordan guarantee is that if you have the RRA for the matrix here on the left hand side, this is automatically your A inverse. So the matrix A inverse is, if you don't have time, you don't have to rewrite it over here. Okay, that's up to you. 72, 14, 5, negative 56, negative 11, negative 4, and 15, 3, 1. Are the inverses always going to be this clean? No. If you just write a random 3 by 3 and start doing things, you will end up with all kinds of wild things there. So these are all specially created to work nicely. Oh, so that should be a bigger smile then. Okay, any questions on this one? So it's a pretty straightforward, but it's a routine question in linear algebra to find the inverse of a 3 by 3. Say, why is this useful? Is this useful in solving a system of equations? Just think about your system or equation from algebra. If you have 5x equal to 3, you could write x equal to 1/5 times 3. Okay. Of course, if this was 0, you cannot do this. So the same thing is applicable here. Okay. If you have a linear system Ax equal to b, where A is a n by n matrix, and now we are dealing with only a square matrix. X is a n by 1 vector. This is x1, x2, x3 up to xn, and this is also an n by 1 vector. So it's a system of linear equations. Can we do something similar there? Just like you divided this 5 on both sides, can you quote unquote divide A on both sides? Okay. The answer is yes. So just multiply A inverse, pre-multiply A inverse, okay, because the order of operation matters here. So pre-multiply A inverse on both sides. And that gives you A inverse times A times X equal to A inverse times B. Because it's an equation, you can multiply both sides by any non-zero number. Okay, so in this case, it's a matrix. A inverse times A by definition is the identity matrix, which is equivalent to a number 1. Okay, anything that multiplies with I will give you the same thing. So the solution X would be equal to A inverse times B. So if you have the inverse matrix, you could pre-multiply it with the right-hand side, and that gives you the solution. Of course, it works only for square matrices, so that's why it's not a universal way of doing things. Okay, this is only for square matrices and if A inverse exists. So, but today we are operating in the world of matrices which have inverses, okay, which is what a lot of engineers believe, that all matrices have inverses. It's not true. Okay, there are all kinds of matrices which have no inverses. So we'll talk about those things later. Okay. All right. So so question of should I start a new example now? Maybe not, okay, because the next one takes a little bit more time. So we'll start tomorrow with a fresh example that finds a 3x3 inverse and also makes use of this. Okay. So, but just to give you a quick intro or quick look at what test 4 will have. Since I did not give many details on my announcement last week, I still will keep the 4 questions. I don't know when I'll break that pattern, but right now it's still 4 questions. Okay. You should know how to multiply matrices. I know it might sound silly, but if you're taking linear algebra and if you're not able to multiply 2 matrices, that's a sad thing. Okay. So there'll be 1 or 2 matrices to multiply and write the answer. Just make sure that you don't forget the compatibility situation. Okay. Solve Ax equal to B or Ax equal to 0. And then write the solution in the vector form. That is what the big chunk of 4.2 and 4.3 is doing, right? So you should identify the basic and free variables, all that jazz. Okay. One of these creatures, so find A inverse for a 3x3 without a lot of stunt. Okay. And also do this one, which we'll do tomorrow. And I'll do an example which kind of solves for X as well, but it's not a big deal. Once you have the inverse, you just have to multiply it. And question 4 is the one I talked about earlier, one of those HK kind of questions. I don't know how to write it clearly, but you know what I'm talking about, the one which said find the values of H and K where the system is consistent, inconsistent. Okay. You may not have all the 3 cases on the test, maybe just 1 case, but that is a type of problem I definitely want you to go over. Okay. Because I just don't want you to be calculation experts and not knowing what you're doing. So that is a critical part of the test. So yeah, those are the 4 questions. So if you haven't started practicing, please do. Okay. All right, so I'll stop there. We'll start tomorrow's lecture with another example with a 3x3 matrix and do this one and then start determinants. Okay. All right, then. If you have any questions, I can stay back. Otherwise, that'll be it for today.
Thank you.
Thank you.